So here's a continuation of chapter 4 on probability. 4.3 talks about complements, conditional probability, and Bayes' theorem. So in 4.3, some key concepts. The first is that we're going to extend the use of the multiplication rule so that it includes the probability that among several trials, we get at least one of some specified event. So with this vocabulary of at least one, we'll talk about how to deal with that. Next, we'll cover conditional probability. So this is the probability of an event occurring when we have additional information that some other event has already occurred. So when we talk about some event being conditional on some other event, this is when we'll get into conditional probability and how to deal with that. The last part of 4.3, we'll do a brief introduction to Bayes' theorem and how it applies to conditional probability. Okay, so to start out, we've previously learned about the idea of complements when dealing with probability, so A and A bar. Here we're going to apply the idea of complements in finding the probability of some event occurring at least once. Let's first talk about what at least once means, or at least one means. When we're talking about this in the realm of probability, at least one has the same meaning as one or more. So it has to happen one time, or it can happen more than that. But it's one time at minimum. Now applying complements, the complement of getting at least one particular event is that you get no occurrences of that event at all. Okay, so it's either one or more, or no occurrences at all. Those are the complements of each other. Now we're going to talk through the steps of finding the probability of at least one. So finding the probability of getting at least one of some event. Number one, we're going to let A, remember A can describe an event. So we'll let A equal to getting at least one of some event. That's our event A. What do you think A bar would be then? If A is getting at least one of some event, A bar, or the complement to that then, would be getting none of that event. Number three, the probability then of A bar, where A bar is getting none of the event being described, then P of A bar is the probability that event A does not occur at all. Remember that probabilities will be 0 to 1 as far as numbers, or 0 to 100%. So using that first set of numbers, 0 to 1, all probabilities, all complements need to add up to 1, right? We covered that last time. So number 4 here, subtract the result from the number 1. This isn't saying step 1, but the number 1 as far as probabilities. Let's look at the expression here for this. So the probability of at least one occurrence of event A is going to be equal to 1 minus the probability that no occurrences of event A are happening. So in this first part here, we're looking at the probability of A. In this second part here, this is our A bar. So the probability of A plus A bar has to equal up to 1. So then rearranging that equation, we can say the probability of at least one occurrence of event A is going to equal 1 minus P of A bar, where A bar is no occurrences of event A at all. Let's do an example. So we have a study from a reputable source. It found that 6% of damaged iPads were damaged by bags or backpacks. So if 20 damaged iPads are randomly selected, find the probability of getting at least one that was damaged in a bag or a backpack. In our answer, we'll also look at this question: is the probability high enough so that we can reasonably be sure of getting at least one iPad damaged in a bag or a backpack? We'll talk about how to answer this. Okay, so here's the setup of our question again. In our solution for step 1, recall the steps that we just went over, I think 2 slides ago. So in step 1, let A, the event A, be that at least one of the 20 damaged iPads was damaged in a bag or a backpack. That's our event A. In step 2 of our solution, we need to determine what A bar means. A and A bar are complements of one another. So here, A bar is going to be not getting at least one iPad damaged in a bag or a backpack among the 20. Right? Because A itself is that we have at least one of the 20 damaged iPads were damaged in a bag or a backpack. Then the complement to this would be that 0 iPads are damaged in a bag or a backpack. That's the same thing here, that all 20 iPads were damaged in a way other than a bag or a backpack. Right? Because A itself is that at least one of the 20 is damaged by a bag or a backpack. The complement to this then is that all 20 iPads were damaged in some other way than that. In our solution for step 3, we need to find the probability of A bar. Recall that we figured out here that A bar is that all 20 iPads were damaged in a way other than in a bag or a backpack. Let's look at the information given in the problem. So this source found that 6% of damaged iPads were damaged by a bag or a backpack. Let's first put this 6% into a non-percentage. So we take 6% divided by 100, or move the decimal point over 1, 2 times to the left, we get 0.06. This is not yet solving for the probability of A bar. This is using what we have in the question to then eventually solve for the probability of A bar. So in other words here, from the information in the question, the probability of selecting an iPad that is damaged by a bag or a backpack out of 100 iPads is 6%. Let me continue on with the solution here and I'll show you. So still from this question, the complement, so 1 minus 0.06 is 0.94. Let's think about what 0.94 really means and what 0.06 really means. 0.06 really means that selecting an iPad just completely at random, the probability that that iPad will be damaged by a bag or a backpack is going to be 0.06. For the complement then, out of those iPads, if we selected 1, then we have a probability of 0.94 that that iPad will not have been damaged by a bag or a backpack. This is how we normally would have dealt with a question like this, but it gets trickier now because we're asking about at least 1. So let's continue on. Remember, we still need to solve for the probability of A bar, but in this special case of at least 1. So remembering our definition of A bar here, the probability of A bar is really the probability of all 20 iPads were damaged in a way other than a bag or a backpack. Now, the probability of selecting one iPad that wasn't damaged by a bag or a backpack, we found out here from the information in the problem, that's 0.94. Here, for this specific problem, our A bar is among all of these 20 iPads because that's what we have in the problem. Then to find our probability of A bar overall, we would take 0.94, so the probability of one iPad not being damaged by a bag or a backpack, multiplied by 0.94 again for that second one not being damaged by a bag or a backpack, multiplied again by 0.94 for the third iPad, and we can continue on for all 20 iPads. What we would end up doing algebraically is that we have 0.94 times 0.94 times 0.94. That's really the same thing as 0.94 raised to the 20th. So putting this all together, the probability of A bar for this specific question is 0.290. We took 0.94 raised to the 20th. I think the tricky part here could be taking information from the problem to then figure out this 0.94 probability and this 0.06 probability. But make sure you're reading the question carefully and following these 4 steps. I had one more note here on your slides. So from the multiplication rule, we would multiply 0.94 times itself for a total of 20 times. So now you have that in your slides as well.
And the reason the multiplication rule is relevant here, because we're really saying the probability of selecting an iPad that was not damaged by a bag or a backpack, and selecting a second iPad that was not damaged by a bag or a backpack, and a third, and so on for 20 total iPads. So really taking 0.94 times 0.94 times 0.94 20 times. So again, that's 0.94 raised to the 20th. So that's that mathematical equivalent.
So we're not quite done with the 4 steps. In step 4 now, we need to actually answer what the question was asking us. So out of 20 damaged iPads randomly selected, find the probability of getting at least one that was damaged in a bag or a backpack. We already figured out probability of A bar. Now we can apply this final step. So the probability of A itself is 1 minus A bar. When we put that all together, we get a probability of A is 0.710. I mentioned when we were solving this that we were going to be able to answer a question like this. So again, we calculated the probability is 0.710. Now we still want to be able to answer, is this probability high enough so that we can reasonably be sure of getting at least one iPad damaged in a bag or a backpack out of those selected 20? Well, let's talk about the interpretation. So for a group of 20 damaged iPads, there's a 0.710 probability of getting at least one iPad damaged in a bag or a backpack. Remember, on our spectrum of probabilities, we can go from 0 to 1. Well, 0.710 is high, but it's not very high. It's not above 0.9, it's not above 0.95. So because this probability is not very high, you'd have to know more specifics on what very high is considered. But here, 0.710, it's not even close to 0.9, it's not really close to 1. So to be reasonably sure of getting at least one iPad damaged in a bag or a backpack out of those selected 20, well, we need to select more than just 20. If we did that, if we selected more than just 20 iPads, then we'd take 0.94 here, raise this to the 30th or the 50th or the 100th, etc. When we raise a number that's less than 1 to a positive power, so 0.94 to the 20th, 0.94 then to the 100th, this number, when it's raised to the 100th, will get even smaller. When probability of A bar is even smaller, that means the probability of A, the event itself, is going to get larger. So coming back here, if we took 1 minus an even smaller number, we're going to get a larger number here. If this number were 0.99, then we could say that's a very high number and we don't need to select any more iPads. In your student outline, there's 2 more examples of this, so as always, let me know if you want to check any of those answers that you get. Next, we're going to talk about conditional probability. So conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. Before we do examples of this, let's talk about the notation. So you've seen this before for the multiplication rule. So here, the probability of event B occurring with a line here, and then A occurring. This denotes the conditional probability of event B occurring. Right? For the multiplication rule, we had to assume that event A had already occurred. So you have seen this notation before for the multiplication rule. Here, we're going to use this notation explicitly when talking about conditional probability. In finding conditional probability, there's 2 approaches, the intuitive approach and the formal approach. We'll talk about both. We'll do an example of both. For the intuitive approach of finding conditional probability, the way we do this is we say the conditional probability of B occurring, given that A has already occurred, can be found by assuming that A has occurred and then calculating the probability that event B will occur. The other approach is the formal approach. Here, the probability of B occurring, given that A has already occurred, so this conditional probability, can be found by dividing the probability of events A and B both occurring by the probability of event A. Mathematically, the calculation looks like this. So this conditional probability of event B based on event A already occurring is equal to the probability of A and B occurring divided by the probability of event A. Let's do an example next using both this intuitive approach and this formal approach for conditional probability. We're going to use a table of data to do the following. So if one of the 555 test subjects is randomly selected, find the probability that the subject had a positive test result given that the subject actually uses illegal substances or drugs. Let's word this as far as probability and as far as events. Remembering our notation for conditional probability, here we're asked to find the probability that the subject had a positive test result, so that's our event B. So here, positive test result, given that the subject actually uses illegal substances. That's our event A that we're going to assume to be true before we find the probability of event B. So the first thing to do with these is to figure out this notation. So the probability of B, so the probability of event B, which is contingent on event A. So we word it like this. Here's this table we're going to use to figure out the answer. In this row here, we have the subject does use illegal substances. Here, if they got a positive test result. Here, if they got a negative test result. If they do use illegal substances and they got a negative test result, that's a false negative test result. The next row here, the subject does not use illegal substances, then 25 of those people actually got a positive test result, that's a false positive, and 480 got the test result they should have gotten if they don't use illegal substances, so they get a negative test result. Let's use the intuitive approach first. Remember from this slide, for the intuitive approach, we're going to assume that event A has occurred and then calculate the probability that event B will occur. So here for this specific example, if we want to assume the selected subject actually uses drugs, we are dealing with only 50 of the subjects in the first row of the table. Then among those 50 subjects, 45 had positive test results. Here's the table, and we can highlight just this first row when using the intuitive approach because we're going to assume that event A is already true. When we assume that event A is already true, then we're just going to use this data here in this first row because event A is that the subject does use drugs. To figure out the probability then of event B specifically, we only need to worry about that now, just looking at this row of data. So event B is, do we have a subject with a positive test result? It's nice because we can narrow it down here to just this first row. So then putting that together, we get the probability of event B contingent on the probability that event A is already true. We only need to look at these 45 individuals that tested positive amongst the 50 individuals here that do use drugs. Then our probability, our final answer using the intuitive approach is 0.900. Now let's try this using the formal approach, so using that formula shown a couple slides ago. When using either the intuitive or the formal approach, we're going to get the same answer. We also do have the same notation here for either the intuitive or the formal approach, so it's still that event B is that we get a positive test result. Event A is that we're assuming that the subject does use drugs. Let's look at the table again so we can see all of our data. Now remember, for the formal approach, we're going to use this equation here. So the probability that event A and B occurs divided by the probability of event A. Let's first talk about the probability of A and B occurring, so to get the numerator here. The probability that event A and B occurs We're looking at the subjects that used drugs and they got a positive test result. That means for the numerator here, the subjects that used drugs here and they got a positive test result means we're only going to count 45 of those subjects. We need to take 45 and divide it by the total number of subjects, so that's 555. That's our numerator here. Let's figure out our denominator. So the probability of just event A occurring. Event A is specifying the subjects that use drugs. To figure out just the probability of A then, we need to look at this first row. So 45 plus 5, that's 50. We take 50 divided by all the subjects present, so that's 50 over 555. Now we have our numerator, the probability of A and B occurring, and our denominator, the probability of just A occurring. We don't have our final answer yet for the formal approach, so then putting this all together, we have the probability of A and B divided by the probability of just A is going to be 45 over 555 divided by 50 over 555. When we put that together, you'll see we still get our same answer as the intuitive approach, so 0.900. Going back here to this slide, we're going to compare the ease of the intuitive approach versus the formal approach. Recall for the intuitive approach, we needed to take one number divided by another number, and then we were done. For the formal approach, we needed to figure out this, and then divide these, and then we were done. So the intuitive approach versus the formal approach, we still get the same answer both times. In comparing the intuitive approach versus the formal approach, it should be clear the intuitive approach is easier to use. Because we have less steps involved, it's also less likely to result in errors. Okay, so now we're able to do both the intuitive and the formal approach to conditional probability, but we'll probably end up doing the intuitive approach more often when given the chance. In the same example, we do have a question B. Here, part B is asking if one of the 555 test subjects is randomly selected, find the probability that the subject actually uses illegal substances given that they had a positive test result. So notice that terminology here that indicates we're looking at conditional probability. The key here is to note that it's saying given that something else is occurring. Using our notation for conditional probability, we need to say that the probability of B is contingent on the probability of event A, where here in the problem, given that they had a positive test result, that's our event A. So they have a positive test result. For event B, it's asking, find the probability that the given subject actually uses illegal substances. That's our event B. So with this conditional probability notation, we have the probability that the subject actually uses drugs, this line here, then the subject had a positive test result. Let's solve for part B. Here we already figured out the notation. Describing this with words now, this is the probability that the selected subject uses drugs given that the subject had a positive test result. If we apply the intuitive approach, then if we're assuming that the subject had a positive test result, we're going to deal with just the 70 subjects that are in this first column of the table. So it's contingent that they had a positive test result. Remember our notation here, so the probability that the subject does use illegal substances given that they had a positive test result. Because this is our event A, then event B is contingent on this being true. Because this is true, a subject had a positive test result, then we just need to look at this column here. In this column here, we have 45 plus 25, that's 70 subjects. Event B in this case, that the subject does use illegal substances, so then we go here to this row where we note that this number is 45 subjects. Putting this information together, we have 45 over 70, so we have this probability of 0.643. That was using the intuitive approach only for part B. Now let's talk about the interpretation of parts A and B together, so putting all the information that we just calculated from this table. In part A, that first result, it told us that the probability of a positive test result contingent upon that subject actually using drugs is equal to 0.900. This indicates that a subject who uses drugs has a 0.900 probability of getting a positive test result. In part B, in the second result, we get a probability that the subject uses drugs contingent on them getting a positive test result is equal to 0.643. This indicates that for a subject who gets a positive test result, there's a 0.643 probability that this subject actually uses drugs. So just slightly different cases here that we calculated the probability for. The wording is really important. These are different questions that were answered here. In other words, note that the probability of somebody getting a positive test result contingent on them actually using drugs does not equal to the probability of a subject actually using drugs contingent on them getting a positive test result. In other words, here in part A, out of all the subjects that use drugs, there's a 0.9 probability they'll get a positive test result. However, here in part B, given that a subject is going to get a positive test result, and then because they actually do use drugs, the probability is only 0.643. This is because of how many false positives there are in these test results. Going back to this table here, you'll note that even for somebody who does not use drugs, out of all the positive test results, 25 actually do not, while 45 do. Okay, so again, just slight differences in what we figured out as far as wording, but we need to be really careful in what we call event A and what we call event B, because you can see when these are switched, we can get very different probabilities and we're actually calculating very different things. That example leads me into this discussion of confusion of the inverse. In that example we just looked at, the probability of getting a positive test result contingent on the subject using drugs does not equal to the probability of the subject using drugs contingent on them getting a positive test result. In other words, these two events are absolutely not inverses of one another. This example helped us prove in general that the probability of B contingent on event A does not equal the probability of A contingent on event B. Now, this isn't to say that there could be individual cases where these are equal, but generally they're not. So to incorrectly think that the probability of B contingent on event A and the probability of A contingent on event B are equal, to incorrectly think they're equal, or to incorrectly use one value in place of the other value when we have the probabilities available to us or we calculated them. This idea is the confusion of the inverse. We don't want to do this. These are not inverses of one another. We don't want to treat them as such. Now let's consider this example of confusing the inverse. So for these two events, we have D where it indicates it's dark outdoors, and M we indicate that it's midnight. In our specific example, we're going to conveniently ignore the Alaskan winters and other such anomalies where it can be midnight yet completely light outside. We're going to ignore those momentarily. So when we write out the probability that it's daylight contingent on it being midnight, that's equal to 1. Again, we're ignoring the anomalies. That means we're saying it's certain, because it has a probability of 1, to be dark, given that it's midnight. Again, we're ignoring these anomalies. Then the inverse of this would be the probability that it's midnight contingent on it being dark outdoors. When we write this notation, we're really saying the probability that it's exactly midnight, so 12 a.m., given that it's dark outside. There are many other times where it's dark outside where it's not midnight. Those many other times outweigh the chance that it is exactly midnight when it's dark outside. So this probability is equal to 1, where it's certain to be dark given that it's midnight. But here, this probability is 0. So the probability that it's exactly midnight given that it's dark outside. This is a clear example where this probability does not equal this probability. If we were to incorrectly confuse the inverse, which we're not going to do, it's where we would incorrectly switch these probability values or think that they're equal, which clearly they're not. Again, what this comes down to is being really careful about what event A is and what event B is, and really thinking critically about the true probability of this event being contingent on this event. Okay, now the last part of 4.3, we're going to talk about Bayes' theorem. So here we're going to extend this discussion of conditional probability that we've been talking about to applications of Bayes' theorem or Bayes' rule. We use this theorem or this rule for revising a probability value based on additional information that's later obtained. I just included this definition here of conditional probability so you'd have it on the same slide. Let's do this example here with interpreting medical test results. In this example, we're going to assume that cancer has a 1% prevalence rate. In other words, 1% of the population has cancer. We're going to denote this event as capital C. So here we have the probability of event C. We take this percentage, we divide by 100, so we have the probability of event C is equal to 0.01. This is the probability for a subject randomly selected from the population. Some other information we need to know for this example. So here, the probability of event C, or an individual having cancer, is 0.01. We got this based on this 1% prevalency rate. One thing that wasn't mentioned here that we need to know is that the false positive rate is 10%. One thing you should be getting used to now is seeing percentages and automatically converting them into non-percent numbers. So given this information, it's saying the probability of a positive test result given that cancer is not present, so this false positive is 0.10. We took 10%, we divided by 100. The meaning of false positive here is saying that the patient does get a positive test result when the patient does not have cancer. Another piece of data here to digest is that the true positive rate is 80%. Again, we'll convert 80% into a non-percentage number. We have 0.80. Using the meaning of a true positive rate, that's saying that the probability of an individual getting a positive test result given that the individual does have cancer. Putting this information together, we're going to answer this: the probability that the patient has cancer contingent on them getting a positive test result. For our solution, we're going to do something we did for the illegal substances example. We're going to make a table from the information we know. To make this table, we're going to have a positive test result. The test shows cancer is present. A negative test result, the test does not show cancer is present. Then in this row, the individual does actually have cancer. Here in this row, the individual does not actually have cancer. When developing this table, one assumption we needed to include was that we have 1,000 subjects total. That makes converting these percentages and these probabilities an easier number to work with. Let's talk through each of these data points and figure out how we got these numbers. Again, we're going to assume 1,000 subjects total with a 1% prevalence rate. 1% of 1,000 is 10. How do we get that? We take this number 1%, move the decimal point over 2 times, we take 0.01 multiplied by 1,000. Here then, we have 10 of the subjects that are expected to have cancer based on this percentage. Now, in setting up our table, the individuals that do have cancer, we know this will total up to 10. Let's keep going through the table now. The other number here, assuming we have 1,000 patients total, that means that the other 990 subjects are not going to have cancer, so we can write this number in at this point. We were also told in the question that 10% get a positive test result. This is among only the 990 subjects without cancer, right? In other words, this was our false positive percentage. So 10% of 990, that's really moving the decimal point over 2 times, that's 1, 2, then we have 0.1 times 990. 10% of 990 then is 99. Remember what this is referring to. These are the individuals that get a false positive result. In other words, the individual doesn't have cancer, but the test is showing that they do. So then we can fill this number in here for 99 subjects. If we know this total now of subjects without cancer, 990, and then we know the individuals that get a false positive test is 99, then 990 minus 99 gives us this number. So from what was just said, we have 891 subjects that get a negative test result and they truly do not have cancer. Next, among the 10 subjects with cancer, that's in the first row, 80% of the test results are positive. We got this 80% earlier from that true positive percentage. Then 80% of 10, how do we find that? We take 80 divided by 100, or we move the decimal point over 2 times to the left. So 1, 2, 0.8 times 10, that's 8 subjects. So then to fill in this part of the table, we have 8 subjects that do have cancer and a positive test result showed that. Now we have one number left to figure out, so we know this total number here, and we know this number here, so then we can get our last value here for the table. So here we figured out that people with cancer, but they tested negative, that means there are 2 of those people that have a false negative test result. The key to filling in this table was assuming an easy total number of subjects, so 1,000 for example, and then really understanding what those percentages mean. Now let's get back to our original question. So we need to find the percentage of patients that do have cancer contingent on them getting a positive test result. Because this is our event A, they get a positive test result, we can focus on just this column in the table. Then event B here is that they do have cancer. Using just this column here, we have 8 patients total that do have cancer amongst the 107 patients total. Then we get our probability here of 0.0748. So truly it is a very good idea to set up a table like this and then try to solve for these probability questions. It may not seem like you have enough information to solve these problems, but then when you write out this table, you realize you can connect more dots than the question originally hints at. So now for the data interpretation. For this data given that we just figured out, a randomly selected subject has a 1% chance of having cancer. How do we figure that out? Well, we have 10 people here that do have cancer. We assumed a total of 1,000 people total. So 10 divided by 1,000, multiply this to get into a percentage, gives us a 1% chance of that subject having cancer. But then for a randomly selected subject given a test with a positive result, so now we're in this column, the chance of cancer increases to 7.48%. That makes sense, right? So now we're narrowing it down to just people that have a positive test result, so that percentage increases to 7.48. How do we get 7.48? Well, this probability was 0.0748. To get this into a percentage, we multiply by 100, or we move the decimal point over 2 times to the right. So 1, 2, that's a percentage of 7.48. So then, based on the data given in this example, a positive test result should not be devastating news because even amongst getting a positive test result, there's still a good chance that the test is wrong. I suppose that's both a fortunate and an unfortunate case of looking at cancer probabilities specifically. The last part of this section is to look at prior and posterior probability. This ties into what we just looked at. So first, let's define this. So prior probability. This is an initial probability value originally obtained before any additional information is obtained. On the other hand, this posterior probability, this is defined as a probability value that has been revised by using any additional information that's later obtained. Let's apply this terminology to our prior example with cancer patients. So here for the prior probability, the probability of a patient having cancer when randomly selected is 0.01 or 1%. This is an example of a prior probability. It's what would have been originally obtained before any additional information is given. So like the false positive and the true positive, for example, that's additional information that we got. So then for a posterior probability applied to that last example, we used additional information we were given that was obtained later, and we found that the probability of a patient having cancer contingent on them getting a positive test result is 0.0748. This is considered our posterior probability because it uses additional information of the positive test result, both false positive and true positive. To truly distinguish between these, you'd have to be told what's the original information we have, and then what do we find out later. That is the end now of 4.3. Let me know if you want to check any of your answers, as always, for any of the student outlines or anything else. I'll see you next time for 4.4.